On a moonless night, far from any highway or house, the Milky Way rises across the sky like a ghostly river of light. It looks solid, endless, peaceful. People once believed this faint arch was the edge of the universe itself, a single ribbon of stars. Yet the more precisely we measure, the less certain we are about what we see. That serene stripe hides dust clouds, shock waves, and the scars of ancient collisions. We live inside a structure we cannot step outside to view. The most familiar galaxy in the sky is, to us, the least known. Here lies the paradox. We photograph galaxies millions of light years away, their spirals bright and sharp, but our own galaxy remains half imagined. How many arms does it have? How thick is its disk? What shaped it? And what continues to stir it even now? Every generation of astronomers has drawn a new map, only to find that the lines must be erased and drawn again. Why does the truth of our home shift so often? What do we keep missing? Imagine trying to sketch your own house while trapped in a single windowless room. You hear the creak of boards, the hum of pipes, the echo of footsteps, but you cannot see the layout. You guess. You draw lines. You think you know the plan. Then a new vibration in the walls reveals another hallway, another stairwell you never imagined. That is how humanity has studied the Milky Way, constructing floor plans from echoes and glimmers. We looked at the heavens and thought we understood spirals, bars, and halos, until better instruments revealed that even our starting point was wrong. From a quiet orbit around the sun, a small metal observatory called Gaia watches billions of stars. It does not see them as pinpoints on a flat sky, but as points moving in 3 dimensions. Every 6 months, as Earth swings to the opposite side of its orbit, stars shift slightly. This parallax lets us measure how far away they truly are, over years. Their subtle drifts trace their motions through space. These twin measurements, distance and motion, are turning our vague sketch of the galaxy into a precise map built from geometry rather than assumption. In everyday language, we are pacing the rooms of our cosmic house at last, counting every step, instead of trusting the guesses of those who drew from memory. The results are both thrilling and uncomfortable. The Milky Way is no calm spiral. Streams of stars stretch through the halo like tidal rivers. Tens of thousands of stars orbit backward, remnants of a smaller galaxy long ago devoured. The outer disk wobbles, lifted by invisible hands. The inner bulge, once thought ancient and settled, contains newborn clusters glowing through the dust. We are discovering that our home is still changing, still alive. To see such motion, astronomers compare data from different instruments. Infrared cameras cut through the dust that blinds optical telescopes. In those wavelengths, the dark lanes of the Milky Way turn transparent, and its hidden heart blazes into view. The VISTA surveys from Chile and the space-based infrared maps reveal crowded corridors where we once drew empty space. Stars fill the void like lanterns appearing in mist. The neat diagrams of a flat, even disk, begin to dissolve. Why does it matter that our galaxy refuses to fit our tidy drawings? Because every conclusion about the universe depends on what we assume a galaxy is. Their light tells us how fast the universe expands, how much matter is hidden, how structure grows from the first atoms. If we have misunderstood the galaxy we inhabit, then the entire scale of cosmic measurement wobbles with it. Radio telescopes add another layer. They listen to hydrogen atoms rather than light. Those whispers outline the galaxy's spine, showing it bent like a warped record, its edges flaring upward and downward. X-ray and gamma-ray detectors reveal enormous bubbles of hot gas shooting above and below the plane. The Milky Way once hurled material outward at almost the speed of light. These relics are not relics of peace, but of power. The galaxy we thought quiet has a violent past. Our perception of normal is built from our limitations. For decades, we selected galaxies that looked balanced and bright for study. Ignoring the lopsided or torn, we assumed the calm spirals were the rule. But the deeper we look, the more we find evidence that chaos is common and calm is rare. Interaction, collision, and consumption are the ordinary states of matter on this scale. The Milky Way is not exceptional in its turbulence. It is typical. Think of a photograph of your own face. Under normal light, you see one expression, but infrared would show blood vessels. Ultraviolet would reveal sun damage. X-rays would show bone. Each layer tells a different truth. The Milky Way under different wavelengths tells a similar story structure beneath structure, patterns that contradict one another, a complexity that refuses a single portrait. Some stars move as if they belong to another time. Their paths tilt and twist against the galaxy's rotation. Some clouds of gas drift opposite to their stars. These mismatched motions are fossils of events that took place billions of years ago. By measuring them, we are reconstructing the family tree of the Milky Way, a story of mergers, cannibalism, and renewal. To put it another way, our galaxy is less a stable island and more a city built on ruins, its streets paved with the remnants of what came before. Even the idea of spiral arms, those graceful lines that fill astronomy textbooks, turns out to be misleading. The arms are not fixed structures. They are patterns in motion, density waves through which stars move like cars through a traffic jam. The shape remains, but the stars come and go. Nothing about the spiral is permanent. It is a pattern of passing crowds. The more precisely we observe, the more we realize that we are part of a system without fixed boundaries. Stars at the edge of the disk leak into space, joining streams that connect to the larger cosmic web. Gas flows inward to feed new generations of stars. Gravity knits and tears, endlessly rearranging the design. What we call the Milky Way is a snapshot of ongoing change, a single frame in an unending film. If this journey through evidence speaks to you, like and subscribe to the Quiet Universe channel. So the question becomes not what the Milky Way looks like, but why it looks this way now. What events shaped its current form? What clues lie buried in the motions of its stars? In the faint whispers of gas? In the symmetry that is almost, but not quite, complete? The answers begin with the oldest evidence of all, the fossil record written in motion, where the galaxy's past collisions still echo through the present. In the early 20th century, astronomers believed they had drawn the Milky Way. They measured the brightness of stars, counted clusters, and concluded that the sun sat near the center of a modest disk only a few tens of thousands of light years wide. It felt complete, a map of the universe, signed by human certainty, but that map was a work of blindness. It was drawn through a fog that no one yet knew how to pierce. The fog was real. Dust, invisible in daylight, filled the plane of our galaxy. It blocked starlight, scattering blue wavelengths, allowing only a faint red glow to leak through. Looking outward from within the disk, observers saw thick clouds of darkness, silhouettes of nothingness. The farther they looked, the less they saw. Yet they assumed that what they could see was all that existed. The first maps of the Milky Way were sketches made from a single candle. In Kansas, an astronomer named Harlow Shapley used globular clusters, those ancient spherical gatherings of stars, as lanterns. He noticed they were not evenly spread. They seemed concentrated in one direction. From that imbalance, he inferred the true center of the galaxy lay far away, hidden behind dust. He was right about the displacement, wrong about the scale. The Milky Way was far larger than anyone imagined. Even so, the idea that we lived near the rim, not the hub, was revolutionary. For the first time, we understood that we were not central even to our own galaxy. Decades later, other astronomers repeated the same error with a new instrument. Radio telescopes replaced visible light, tracing hydrogen gas instead of stars. The first maps of hydrogen emission looked like a flat spiral with 4 neat arms, Artists painted them blue and gold. Posters decorated classrooms. The picture was clear, but the evidence was not. Distance in radio space is tricky. The motion of gas can mimic position. The elegant spiral may have been an artifact of our methods, a projection of expectation rather than reality. Why do we cling to patterns that may be illusions? Perhaps because we need the universe to look finished. A neat spiral is comforting, proof that nature follows simple geometry. But as new surveys arrived, the spiral fractured. 2 arms became 4, then 3, then 2 again depending on which wavelengths were used. Some tracers followed old stars, others young ones, others gas and dust. No 2 agreed. Think of explorers charting a continent without ever leaving the shore. One measures the tides, another the shape of migrating birds, another listens to the wind. Each produces a different outline, and each claims to have found the true coast. That is what mapping our galaxy has always been like. We cannot leave our position inside it, so every method is indirect. An echo. As technology improved, the echoes multiplied. Infrared surveys looked through dust and found entire arms of the Milky Way hidden from view. Optical telescopes, freed by adaptive optics, corrected for the turbulence of Earth's atmosphere and revealed millions of new stars. Space telescopes extended our reach beyond the veil, measuring regions never seen before. Yet even with all this data, the overall shape of the Milky Way remains a sketch that shifts with every update. Why does this uncertainty matter? Because structure tells history. A warped disk implies tidal forces from a past collision. A thickened bulge suggests ancient mergers. A population of stars moving opposite to the rest hints at cannibalism. Every twist of the map encodes a story. Without knowing the real structure, we cannot read the story correctly. To put it another way, we are archaeologists digging in the dark. The stars are fragments of pottery scattered in layers of dust. Each must be dated, each placed in context, but the layers are mixed and disturbed. What we call the Milky Way today is the visible surface of countless buried events. The European Gaia mission changed the game by giving distance and motion for over 1 billion stars. With those coordinates, the galaxy can be reconstructed in 3 dimensions, not as a flat diagram, but as a living structure. The illusion of symmetry begins to collapse. The sun sits in a minor spur between larger arms, a mere eddy in a galactic current. Stars around us follow slightly different paths, revealing gravitational ripples that betray old impacts. In everyday language, the Milky Way is less a wheel and more a river delta, always moving, always shifting its channels. But even Gaia is limited. Its precision fades through the dustiest regions. Infrared missions such as WISE and VISTA pick up where Gaia falters, mapping stars hidden in the central bulge. Combined, they produce a more complete picture. Yet the more complete it becomes, the less it resembles the diagrams we once trusted. The spiral arms are not tidy ribbons, but irregular waves of density. The disk thickens, folds, and twists. The center glows with overlapping populations of stars of wildly different ages. There is a deeper irony. The better our instruments, the more incomplete our sense of certainty becomes. Every new survey solves an old puzzle but introduces 2 new ones. If knowledge grows, so does confusion. Why it matters is simple. Our galaxy is the template we use to understand others. When we misjudge its form, we distort every cosmic measurement built upon it. The distances to other galaxies, the rate of expansion of the universe, the balance of visible and invisible matter, all rest upon assumptions rooted in our local map. The errors we make here echo outward to the edges of cosmology. The cartographers of old drew dragons at the borders of their maps, warnings that beyond this line lies the unknown. In our new star maps, the dragons are inside the line. They live in the regions we thought we understood best. At its core, mapping the Milky Way is a test of humility. Each improvement in data reminds us that we are still drawing blindfolded. The only honest map is one that leaves room for revision. If the night sky appears serene, It is only because we view it through the slow filter of time. Stars drift a few kilometers per second, imperceptible to our eyes but vast across millennia. The galaxy changes shape as we speak. What we call permanent is merely slow. The constellations our ancestors drew will vanish. The spiral arms will rearrange, and the Milky Way of the far future will not match the pictures we make today. We can no longer claim ignorance as an excuse. The instruments exist. The data streams in daily. It is we who must learn to see without the comfort of simplicity. The fog that hides our galaxy is not only dust but expectation. To clear it, we must surrender the image of perfection and let the evidence draw its own lines. The next step in that surrender comes when we examine the remnants of what the Milky Way has consumed. For only by reading the debris of its meals can we trace how it grew into the giant we inhabit today. Every galaxy grows by consuming others. It sounds violent, but in cosmic terms it is ordinary. Gravity is patient, and over billions of years it pulls small systems toward larger ones until their stars mix. Their gas is stripped, and their histories merge. The Milky Way is no exception. Its calm appearance hides a record of devoured neighbors. If the galaxy could keep a diary, it would be written in collisions. Astronomers once pictured the Milky Way as a solitary island adrift in dark space, self-contained and undisturbed. That view began to crumble when precise measurements of star motion arrived. In the data from Gaia, hundreds of thousands of stars refused to behave. Their orbits tilted against the plane of the galaxy. Their speeds and directions broke the expected pattern. They formed a ghostly halo moving against the grain. Somewhere in that turbulence lay the fingerprint of an ancient merger. The story began to emerge when scientists traced those odd orbits backward through time using computer simulations. The stars converged into a single ancestral structure, a smaller galaxy that had collided with ours roughly 8 to 11 billion years ago. It was given a name, but the label matters less than the act itself. That impact reshaped the Milky Way. The collision stirred the thin disk into a thicker one, scattered stars far above the galactic plane, and may have triggered a burst of star formation that gave rise to our Sun. Simply put, the Sun and Earth may owe their existence to an act of cosmic cannibalism. Why it matters runs deeper than curiosity. A galaxy's mergers set its chemical makeup and its potential for habitable worlds. When one system swallows another, it absorbs not just stars but their elements, the oxygen and carbon and iron that future generations of stars will inherit. Every breath of air, every trace of metal in our bodies, is a line item in that ancient ledger. The evidence is not confined to motion. Chemistry tells the same tale. Stars born in different galaxies carry distinct ratios of elements, a signature of the environments they formed in. When astronomers plot those ratios for millions of stars, a new pattern appears: two overlapping populations. One matches the Milky Way's native stars. The other bears the chemical accent of a foreign origin. These chemical immigrants form vast streams that encircle the galaxy like ghosts of the swallowed. In plain terms, the Milky Way's halo is a graveyard. Each ring of stars is a tombstone marking the orbit of a galaxy long gone. One of the clearest remnants arcs across our sky as a stream of stars known for its persistence. It stretches tens of degrees, a ribbon of suns torn from their parent galaxy as it spirals into ours. Another remnant hides in the southern sky, a dwarf companion still in the act of being devoured. Its orbit carries it through the Milky Way's disk every few 100 million years, shaking our galaxy like a bell. These encounters raise waves in the disk, creating ripples that we can still measure. The Sun sits within one of those ripples. Some models suggest that a past passage of this dwarf companion may have compressed gas clouds near the Sun's birthplace, setting off the chain of star formation that ultimately produced our system. If so, our existence is the delayed consequence of an encounter between two galaxies. The cannibal's meal gave rise to the diners. Astronomers track these mergers through star streams, each a strand in the larger weave of galactic history. The most ancient streams fade as their stars mix. leaving only subtle patterns in motion. Younger ones remain visible, bright scars against the dark. Mapping them requires immense data sets, not only from Gaia, but from infrared and spectroscopic surveys that measure stellar velocities and compositions. Piece by piece, the ledger fills in. Yet the total is not fixed. New analyses continue to uncover structures we did not expect. A cluster of stars moving together might be the core of a swallowed dwarf. A warped distribution in the outer disk could signal a still hidden companion tugging from beyond. Some models predict that even now, faint satellites are orbiting unseen, their gravity quietly shaping our future. To put it another way, the Milky Way is still eating. The meal never ends. What does that say about galaxies themselves? Are they individuals, or are they ecosystems that consume and recycle endlessly? Each merger erases boundaries, turning separate histories into one. The atoms in our blood were likely forged in stars from multiple ancestral galaxies, mixed by violence, preserved by time. We are not residents of a single galaxy, but inheritors of several. Consider the scale. When two galaxies merge, their stars rarely collide directly. The distances are too vast. Instead, their gravity stirs the mix. Gas clouds compress, birthing new generations of stars. At the same time, the central black holes spiral together, radiating energy as they close the gap. Eventually, they merge into one larger black hole, releasing gravitational waves that echo across space. Each collision is both destructive and creative. In human terms, it is like watching cities collide. Buildings crumble, debris scatters, but from the wreckage rise new streets and new architectures that borrow pieces of the old. The Milky Way's thick disk, composed of stars older than the Sun and higher above the galactic plane, is one such reconstruction. Its formation coincides with the timeline of that major merger. The orbits of its stars show random tilts, remnants of the violent stirring. These are the debris fields of that ancient event, still visible after billions of years. Some astronomers argue that even the bar at the center of the galaxy, the elongated cluster of stars crossing the core, may have been seeded by these collisions. The inflow of energy and material could have reshaped the core into its present form. Others suggest that repeated impacts with dwarf companions later reinforced the structure, keeping the Milky Way in motion like a spinning top constantly nudged by unseen hands. Why it matters goes beyond galactic anatomy. The pattern of mergers defines how galaxies evolve across cosmic time. When we trace the Milky Way's record, we gain a template for understanding the rest of the universe. Large surveys show that galaxies similar to ours are still merging at comparable rates. The act of cannibalism is not an exception. It is the heartbeat of cosmic growth. Think of it like this. Galaxies are farmers of their own futures, plowing neighboring fields of stars to sow the seeds of new generations. Without mergers, star formation would slow, elements would stagnate, and complexity might never rise to the level required for life. Violence and creation are intertwined. We live in the long afterglow of those ancient encounters. The night sky, filled with steady points of light, is the calm surface of an ocean still moving beneath. If we could see with the right instruments, we would notice every star tracing the memory of its origin, some circling peacefully, others looping through vast arcs that remember a different home. Some teams suggest that one more significant merger may still be ahead of us. A small nearby galaxy, rich in dark matter, is predicted to merge fully within the next billion years. Beyond that, the larger spiral of Andromeda approaches inexorably. In 4 billion years, the two great systems will collide and fuse into one. The ledger will close only to open anew under a different name. At its most profound, the Cannibal's ledger is not a list of destructions but of continuity. Each galaxy swallowed becomes part of the next. Each collision recycles matter into new stars, new planets, new chances for life. Our galaxy is a mosaic of the dead, shining with their remains. We cannot yet read every entry, but the handwriting is clear creation built on consumption, beauty born from ruin. The ledger balances itself, The next clue lies in what happens to the light trapped behind the dust at the galactic center, where youth and age coexist in impossible proximity, challenging every notion of how a galaxy grows. At the center of our galaxy lies a paradox older than our instruments: the bulge. A swollen core of stars packed more densely than anywhere else in the Milky Way was long believed to be ancient. Its stars, red and dim, whispered of age. Dust veiled the region so completely that for most of history it was invisible in ordinary light. When the first infrared telescopes began to pierce that shroud, astronomers expected only to confirm what they already believed. Instead, they found signs of youth. Hidden behind the veil was a network of bright stars pulsing with regular rhythms, the kind of stellar heartbeat that marks youth and vitality. These were classical Cepheids, stars only tens of millions of years old, flickering in predictable cycles. Their discovery was not a small correction, but a contradiction. The core of the Milky Way, supposedly a relic of the early universe, was still forming stars. Something had rejuvenated it. The finding raised immediate questions. How could young stars exist in a region thought to have burned out eons ago? Where did the fresh gas needed for their birth come from? If the bulge was an archive of the past, what mechanism had rewritten its pages? To understand, astronomers had to look deeper through the dust and into the motion of the stars themselves. Infrared surveys such as VISTA and Spitzer mapped the bulge with increasing clarity. The veil became translucent, revealing an intricate structure. The central region was not spherical, as older models assumed, but shaped like a bar with a peanut-shaped cross-section. Streams of stars traced an X pattern, the fossil of dynamic instabilities that had rearranged the galaxy's heart. Amid this intricate structure, rivers of gas still flowed. At its core, the bulge was not a dead monument. It was a living organ connected to the disk by veins of material. These veins funneled gas inward from the spiral arms, feeding the central regions and sustaining new star formation. The supposed barrier between the youthful disk and the aged bulge was an illusion created by dust and perspective. In plain terms, the heart of the Milky Way is still breathing. This realization changed more than one model. If gas can stream inward across tens of thousands of light years, then the cycle of star formation and death inside a galaxy is more continuous than we thought. The galaxy does not evolve in isolated chapters of youth and age. It recycles, drawing in the debris of previous generations to ignite new ones. The young Cepheids in the bulge act as tracers, neon signs of this hidden circulation. Their distribution outlines a thin midplane slicing through the old core, evidence of a thin disk of stars that threads the central bulge. This discovery erased the clean boundary between inner and outer regions. The Milky Way is not divided between young and old, but braided together like strands of time. Why does it matter? Because this dynamic core may explain features we see in other galaxies. Many barred spirals show bursts of star formation near their centers. Until recently, those were treated as exceptions or temporary phases. Now we see that the Milky Way is undergoing the same process, a low-level but persistent regeneration. Our galaxy's center may flare and fade like a hearth that never entirely cools. The existence of young stars in the bulge also implies something about our galactic environment. The flow of gas into the center requires gravitational channels, created by the rotation of the bar and the spiral arms. These structures act like cosmic plumbing. Without them, gas would remain trapped in the disk, and the bulge would remain dormant, the balance between inflow and feedback gas pouring in. Radiation and winds pushing out determines the rhythm of galactic life. Simply put, galaxies are engines, and the Milky Way's heart is still running. We cannot see these processes directly, but we can trace their fingerprints. Radio observations reveal molecular clouds near the core, dense and turbulent, perfect sites for future star birth. X-ray data shows the scars of past outbursts, bubbles of hot gas rising above and below the plane, remnants of periods when the central region flared with energy. These are not separate events. They are stages in the same cycle. To put it another way, The bulge is both cemetery and nursery, holding the ashes of old stars and the cradles of new ones side by side. This duality unsettles the old picture of galaxies aging gracefully. Instead, they pulse between decay and renewal. The Milky Way, seen through infrared eyes, glows with veins of youth threading its ancient frame. The discovery challenges our assumptions about stability and age, showing that even structures billions of years old can still surprise us with vitality. Consider the human parallel. Our planet orbits a middle-aged star, itself a product of long-dead predecessors. Life emerged not in the quiet of old age, but in the chaos of recycling. In the same way, the galaxy's core seems to thrive on disorder, drawing strength from the remains of its own history. There is a philosophical echo in that observation. If the center of our galaxy can host both the oldest and youngest stars together, then perhaps the universe itself never settles into a single age. The cosmos is not a sequence of distinct eras, but a conversation between them. Youth and age coexist, and their interplay creates the structures we see. Scientists continue to refine the map of the bulge using data from multiple wavelengths. Each new survey brings sharper resolution, yet each reveals more complexity. The young populations are not evenly spread. They cluster along the bar, following patterns that hint at gravitational resonances. The more we learn, the more intricate the dynamics become. The heart of the Milky Way behaves like a living ecosystem, full of feedback loops and self-regulating mechanisms. Why it matters reaches beyond our galaxy. Understanding how the bulge stays active informs models of galaxy evolution across the universe. When we observe distant galaxies in different stages of life, we are often seeing analogs of our own core at various points in its cycle. The Milky Way becomes a laboratory for understanding cosmic metabolism, how energy and matter flow through vast systems over billions of years. Think of it like this: each new star born in the bulge is a word added to an endless sentence that began when the first atoms formed. The sentence is never finished. It continues to write itself through time. Even with this clarity, mysteries remain. What triggers the inflow of gas at particular times? Is it the gravitational tug of a passing satellite galaxy, or internal resonances within the bar? Why does star formation in the bulge seem episodic, switching on and off over millions of years? These are open questions, the next lines waiting to be written in the galaxy's chronicle. In all of this, one theme repeats: nothing in the Milky Way is as static as it appears. The veil of dust that once hid the core also hid the truth that renewal is a constant state. When we finally lifted that veil, we did not find the quiet of old age, but the pulse of youth. The next mystery lies outward in the spiral arms themselves, where patterns of stars hold their form without solid structure, challenging the very idea of motion and permanence. From a distance, spiral galaxies look serene. Their luminous arms curl outward like shells, as if frozen in a graceful dance. The Milky Way is pictured this way in textbooks, a vast wheel turning slowly through space. But when we look closer, the illusion begins to crumble. The arms of a galaxy are not solid, and they are not permanent. The stars inside them come and go, moving through the pattern as if through waves on water. The spiral, for all its elegance, does not truly spin. The first hint of this paradox came from mathematics. If the stars in a galaxy orbited the center like planets around a sun, the inner ones would move faster than the outer ones. Over time, the spiral arms would twist tighter and tighter, winding up until they disappeared. Yet the arms remain. They hold their broad, open shapes for billions of years. Something must be maintaining them. Something that moves slower than the stars themselves. In everyday language, the arms of a galaxy are traffic jams in a cosmic highway. Cars enter and leave, but the jam itself stays roughly in the same place. This idea, known as the density wave model, was one of the most elegant solutions in modern astronomy. It suggested that the spiral arms are regions of slightly higher density that move as waves through the disk, compressing gas and triggering star formation as they pass. Stars are born bright and blue within the waves. then drift out as they age and fade, giving the illusion of motion along the arm. Yet even this elegant theory meets contradictions. When astronomers measure the pattern speeds of spiral arms in different galaxies, they find wide variation. Some arms seem to rotate faster, others slower, and some show evidence of breaking or branching. In our own Milky Way, the pattern is especially hard to define because we see it from within. Infrared surveys show two main arms, while radio maps of hydrogen and carbon monoxide trace four or more. Different tracers reveal different shapes. Young stars align along one set of spirals, old stars along another. Which of these, if any, is the true structure? The answer may be that none are permanent. Think of the Milky Way's arms as standing waves in a pond stirred by many pebbles. Each pebble is a gravitational disturbance, perhaps from a passing satellite galaxy or a ripple left by an ancient merger. The waves overlap and interfere, sometimes amplifying each other, sometimes canceling out. The pattern we call an arm is the temporary alignment of these ripples, lasting for hundreds of millions of years, but not forever. Why does this matter? Because it means our galaxy is not a rigid mechanism, but a living pattern, constantly reorganizing itself. The beauty we see in the night sky is a snapshot of turbulence caught in slow motion. The density wave model, once dominant, now competes with another explanation: dynamic spirals. In this view, the arms are transient features generated by the combined gravitational pull of stars and gas, forming and fading continuously. Simulations that include realistic physics produce such arms naturally, without the need for a long-lived wave. They appear, stretch, and dissolve as material flows through the disk. At its core, the spiral is not a structure but a rhythm. Our understanding of this rhythm comes from measuring how stars move. The Gaia mission's data shows that stars in the disk do not follow perfect circles. They oscillate in and out, up and down, responding to subtle variations in gravitational pull. When mapped in detail, these oscillations trace patterns that align with the spiral arms. They are the signatures of waves passing through the galactic disk. Simply put, the Milky Way hums, and the spirals are the shape of its music. The role of gas is crucial. Gas clouds feel gravity more strongly than individual stars because they are dissipative. They can cool, condense, and lose energy. As they pile into a spiral wave, they collide, compress, and ignite new stars. Those young stars, luminous and short-lived, light up the arm when they die. Their explosions stir turbulence that may generate the next wave. Thus, the spiral arms are both cause and consequence of star formation, a feedback loop of motion and renewal. Why it matters extends beyond elegance. These density patterns influence the stability of planetary systems, the distribution of cosmic rays, and the rate at which heavy elements spread through the galaxy. Even the environment around the Sun depends on where we are relative to the spiral arms. Some models suggest that our solar system crosses an arm every 100 million years or so, possibly altering the flux of comets and radiation that reaches Earth. The rhythm of the galaxy may subtly shape the rhythm of life. The mystery deepens when we look beyond our galaxy. Some spirals, such as NGC 4622, appear to have arms that lead rather than trail the direction of rotation. Others show gas rotating opposite to their stars, as if two systems have merged but never fully mixed. These anomalies hint at histories of interaction and disruption. No two spirals are the same because no two pasts are alike. To put it another way, the spiral is the memory of motion, a pattern written by every encounter the galaxy has ever had. Observations of edge-on galaxies reveal another layer. Many show vertical ripples, bends, and flares in their disks. These are not aesthetic quirks, but the echoes of gravitational encounters, waves still traveling through the galactic plane. Our own Milky Way displays similar warps, traced in the motion of outer hydrogen gas. the entire disk undulates, as if the galaxy were a sheet of fabric caught in a slow breeze. When computer models include the influence of nearby dwarf galaxies, the picture becomes clearer. Each encounter sends waves through the disk, and those waves can reinforce or distort the spiral pattern. The Milky Way's persistent but imperfect spirals may owe their shape to the continuing influence of these small companions. At its most fundamental level, the spiral arms remind us that galaxies are not static islands of matter, but resonant systems governed by feedback and instability. The universe achieves its beauty not through stillness, but through balance between chaos and order. If we could accelerate time, the Milky Way's arms would shimmer, break, and reform endlessly, like auroras rippling across the sky. The illusion of a steady wheel would vanish, replaced by a dance of light and shadow flowing through the dark. The spiral that does not spin would reveal its true nature as a heartbeat of gravity and time. So the next time you see an image of a galaxy, remember that what you are seeing is not an object but a performance. The arms are choreography, the stars are dancers, and the stage is the void. Every frame hides centuries of movement, every photograph a frozen note in an endless composition. The next mystery waits in the small, furious engines scattered across the galaxy, where collapsing stars mimic the power of quasars and hint that the secrets of the largest structures may be written in the smallest machines. Deep in the Milky Way, certain stars behave as if they were galaxies in miniature. They flare, feed, and launch jets that pierce the surrounding darkness. These systems are called microquasars, small-scale versions of the titanic quasars that blaze at the centers of distant galaxies. Their energy comes from the same process, matter falling into a black hole, but on a humanly imaginable scale. By studying them, we can learn about forces too distant and too vast to touch otherwise. The story begins with a binary star. One of the pair has died, collapsing into a black hole, or a neutron star. The survivor orbits close enough that its outer layers are pulled toward the corpse. Gas spirals inward, forming a disk around the compact object. Friction in this disk heats the gas to millions of degrees, causing it to shine in X-rays. But not all the matter falls in. Some is ejected outward at nearly the speed of light, forming twin jets that extend for light years. At first glance, these jets seem too energetic to come from a single star. Yet when radio telescopes observed them, they saw them moving outward in real time, a rare gift in astrophysics. The system known as SS433 became the archetype, its jets precessing like a wobbling top. Shifting direction over months, each jet carries streams of plasma traveling at a quarter of the speed of light. The power source is gravity itself, turning infalling matter into energy with an efficiency far beyond any chemical or nuclear process. In plain terms, a black hole is the most efficient engine the universe allows. The physics at work inside the accretion disk is extreme. Magnetic fields twist and tighten, guiding charged particles into the jets. Shocks within these flows accelerate electrons to tremendous speeds. When those electrons collide with photons from surrounding starlight, they boost the light into the gamma-ray range through a process called inverse Compton scattering. This chain of events turns gravitational energy into radiation that can outshine the entire star system. Why it matters is simple by watching microquasars nearby. We test the same laws that govern the colossal quasars at the hearts of distant galaxies. The advantage is proximity. Instead of watching a galaxy-sized monster evolve over millions of years, we can observe a microquasar change within days or weeks. Every flare, every flicker of X-rays, becomes a miniature version of a cosmic event scaled down by factors of a billion. To put it another way, microquasars are laboratories where relativity, magnetism, and plasma physics meet face to face. Take the case of the jets themselves. How can something escape from the vicinity of a black hole, where gravity is so strong that not even light can leave once it crosses the event horizon? The answer lies just outside that boundary. The rotating black hole drags space around with it, winding magnetic fields into tight coils. Those fields act like springs, flinging charged particles along the poles of rotation. The result is a pair of jets that appear to defy gravity, but are in fact powered by it. These jets interact with their surroundings, inflating bubbles of hot gas visible in radio and X-ray light. They carry enough energy to sculpt the interstellar medium, triggering or suppressing new star formation depending on where they strike. In this way, even a single microquasar can influence its neighborhood across dozens of light years. The lesson scales upward. The same feedback mechanism operates in galaxies and clusters, where giant black holes regulate the growth of everything around them. At its core, feedback is the universe's way of enforcing balance. Too much gas falls inward. The jets flare, heat the surroundings, and push the gas away. Star formation slows until the system cools again. Then the cycle resumes. Galaxies breathe through their black holes, and microquasars are the small lungs through which we can watch that breathing directly. Observations of microquasars also challenge our sense of time. The accretion disk brightens and dims as if alive, fluctuating on scales of seconds to hours. These flickers trace turbulence close to the event horizon, where matter orbits at nearly light speed. When we record these variations, we are effectively timing the heartbeat of a black hole. Each beat reveals how fast the black hole spins and how space-time itself is distorted in its grip. Simply put, microquasars translate cosmic grandeur into human tempo. There is another connection. The gamma rays emitted by their jets reach energies in the tens of trillions of electron volts. Detecting such light requires specialized observatories on Earth and in orbit. When those photons arrive, they carry information about the processes that accelerate particles throughout the cosmos. Understanding microquasar jets helps explain cosmic rays that strike our atmosphere, linking the smallest systems to phenomena that touch our own planet. Why it matters again surfaces here. Energy transport on these scales determines how galaxies evolve. The same equations that describe the jets of SS 433 apply, with adjusted parameters, to the outflows of quasars billions of light-years away. By perfecting our understanding of the small, we clarify the behavior of the immense. Think of it like this: a microquasar is a candle whose flame mirrors the furnace of a galaxy's heart. The analogies extend to structure. Just as galaxies have accretion disks around their central black holes, so too do microquasars around stellar remnants. Both produce jets that carry angular momentum away, allowing matter to continue falling inward. Both radiate across the electromagnetic spectrum, from radio to gamma rays, and both display the same scaling relations between mass, power, and variability. The cosmos repeats its patterns at every level, fractal in behavior if not in form. Some researchers suggest that studying the precession of microquasar jets may help test general relativity itself. As the black hole spins, it twists nearby space, a phenomenon known as frame dragging. The wobbling of the jet axis in SS 433 provides one of the clearest indirect signatures of this effect. We cannot fly probes to distant supermassive black holes, but we can watch their miniature counterparts perform the same dance in our own galaxy. At its core, the lesson is humility. Nature does not need grand scale to demonstrate grandeur. The same equations that govern the most luminous quasars unfold silently in a system small enough to fit within a single pixel of the Milky Way. As technology improves, more microquasars reveal themselves. Sensitive radio arrays and high-energy detectors uncover faint jets previously hidden in noise. Some emit bursts that last mere hours. Others maintain steady outflows for decades. Each adds another data point to the universal rule: wherever matter falls into deep gravity, order emerges from chaos. The connection between these small engines and the galaxy at large is more than metaphor. The energy they inject helps maintain the balance of gas and stars in the Milky Way. Without such feedback, the galaxy might have collapsed into uncontrolled star formation long ago. The tiny shapes, the vast. If galaxies can be said to think, microquasars are their synapses, transferring information through bursts of radiation across cosmic time. There is poetry in that image. A dying star, reduced to a black hole, becomes an engine for creation elsewhere. Its jets sow energy into the interstellar medium, influencing the birth of stars yet to form. Destruction feeds renewal, on scales we can barely imagine. In studying these compact systems, we are reminded that even the smallest corners of the universe mirror its grandest designs. The Milky Way's microquasars whisper lessons about balance, scale, and repetition. Each is a local experiment in cosmic architecture. The next step leads outward again, to the colossal black holes that lit the early universe, the young giants whose rapid growth still puzzles science, and whose light reached us across the longest distances of all. When astronomers look deep into the early universe, they find a puzzle shining at the edge of time. Only a few 100 million years after the Big Bang, supermassive black holes already existed, some weighing billions of solar masses. Their light, amplified by the matter falling into them, outshines entire galaxies. They are the quasars of the dawn era, and their presence defies simple growth models. How could something so enormous have formed so quickly in a universe still young and thin? The discovery of these ancient giants came from the combined power of large telescopes and careful sky surveys. Each quasar appears as a bright point, its spectrum stretched by cosmic expansion into redshift. The farther we look, the younger the universe appears, and yet the quasars remain massive. They force us to confront a question of speed. Gravity builds black holes steadily, but time in the early universe was short. Somewhere, a hidden mechanism must have accelerated their birth. In everyday language, it is like finding skyscrapers already standing while the foundation of the city is still being poured. The first theories tried to stretch known physics to fit the data. Perhaps these quasars began as the remnants of the very first stars, the so-called population 3 generation, massive and short-lived. When they died, their cores collapsed into black holes tens of times the mass of the Sun. Given enough time and fuel, such seeds could grow through accretion and mergers. The problem is time. From the birth of those first stars to the epoch when we observe the brightest quasars, there are not enough millions of years to grow them by ordinary means. Other models propose that some black holes formed directly from collapsing gas clouds without ever becoming stars. In regions where cooling was inefficient, whole clumps of primordial gas might have fallen inward to form black holes of 100,000 solar masses in a single collapse. These direct collapse seeds would have a head start, needing only moderate accretion to reach the observed sizes. Evidence for such events remains indirect but plausible. To put it another way, the early universe seems to have been capable of shortcuts. A related puzzle lies closer to home. The supermassive black hole at the center of our Milky Way, about 4 million solar masses, is modest compared to those early giants. It feeds slowly now, but traces in X-ray and gamma-ray data suggest it once flared much more brightly. Giant bubbles of high-energy gas above and below the galactic plane may be relics of those outbursts. If our galaxy's black hole was once more active, it could represent a later echo of the same processes that powered the earliest quasars. Why does it matter? Because understanding how these black holes grew tells us how galaxies themselves formed. The growth of a central black hole and the growth of its host galaxy appear linked. As the black hole feeds, its jets and winds influence star formation across thousands of light years. If the hole grows too fast, it can blow away the gas that would make new stars. If it grows too slowly, the galaxy remains small and dim. The balance between the two shapes the cosmic landscape. Simply put, galaxies and their black holes co-evolve, each feeding the other. Observations from space telescopes have added to the mystery. The James Webb Space Telescope revealed galaxies in the early universe, more massive and structured than expected, containing heavy elements only possible after many cycles of star birth and death. Such maturity so soon after the beginning suggests that star formation and black hole growth were far more efficient than our models allow. Either the early cosmos produced stars and black holes at furious rates, or we have misunderstood the physics of accretion itself. Think of it like this. The universe's first lights did not flicker into existence gently. They ignited like wildfires. Some researchers point to the density of gas in the young universe as a clue. Matter was packed more tightly, and collisions between galaxies were frequent. Those interactions could have funneled enormous streams of gas toward central regions, feeding black holes faster than they can today. Other teams note that radiation pressure may not limit growth as strictly as once thought. Under certain conditions, accretion disks can remain stable even when bright enough to exceed classical limits. If that is true, black holes could have grown faster than our earlier calculations allowed. At its core, the question of the youngest giants is a question about limits. How fast can nature build complexity before physics says stop? There is also the issue of detection bias. The quasars we see are the brightest because they are the easiest to find. Fainter ones, less massive or less active, may be hidden below current sensitivity. This bias makes it seem as if the early universe was dominated by monsters when, in reality, it may contain a spectrum of black holes in various stages of growth. The most extreme examples catch our attention, but they might be rare peaks in a much larger population. Why it matters again reaches into our understanding of cosmic history. The first quasars likely played a key role in transforming the universe from opaque to transparent. Their intense radiation helped reionize the gas between galaxies, allowing light to travel freely. Without their energy, the universe might have remained shrouded in neutral hydrogen for much longer. The young giants did not merely exist, they changed the environment for everything that followed. In plain terms, they switched on the lights of the cosmos. Yet their very brightness poses a riddle. If they were so luminous, how did their host galaxies survive? The energy released by accretion could have blown away the gas needed for further star formation. And yet, galaxies continued to grow. It seems that feedback from black holes can both hinder and help, clearing paths that later allow gas to cool and fall back in. Destruction and creation, again intertwined. The phenomenon known as the Malmquist bias adds another layer. Our surveys preferentially detect the brightest objects, which skews our sense of the average. We may be building our picture of the early universe from outliers, the flamboyant exceptions rather than the rule. If we could see everything, the story might look more gradual, less explosive. But until our instruments grow sensitive enough, the youngest giants will dominate our view, standing as beacons of extremes. To put it another way, the early cosmos is an artist that paints only in bold strokes. Our fascination with these quasars is not just about numbers. They embody the tension between time and possibility. In them, we see the universe testing its own rules, assembling colossal structures faster than should be possible. They remind us that creation, at any scale, is rarely gentle. The same forces that drive galaxies to brilliance also contain the seeds of collapse. Why it matters for us lies in perspective. We live in a calmer era of the cosmos, but the principles remain: the balance between growth and feedback, between matter falling in and energy pushing out, continues to shape every level of structure, from star clusters to the Milky Way itself. The youngest giants teach us that stability is temporary and that change, not order, is the natural state of the universe. If the first black holes were the forges that lit the early sky, then their descendants are the keepers of that flame, ensuring that the cosmos remains dynamic. The great mystery is not only how they grew so fast, but how they kept the universe interesting. The next step turns our attention to the strangest galaxies of all, those that bend light into arcs and circles, revealing the unseen skeleton of the cosmos and the scale of its hidden mass. Every map hides its exceptions. As astronomers cataloged galaxies across the sky, they began to notice the ones that refused to fit any pattern. Some spirals had arms curling in the wrong direction. Some ellipticals contained rings of dust like smoke trapped in glass. Others stretched into long filaments, connected to companions millions of light years away. These outliers became the most valuable entries in a growing atlas of the peculiar, because it is often the exceptions that tell us what the rules truly are. The first of these oddities were found on photographic plates from early telescopes. The human eye was drawn to symmetry, so these strange shapes stood out. Two galaxies locked together, their arms flung outward as if in a frozen embrace. A lens-shaped system surrounded by perfect concentric rings of light, a small galaxy half swallowed by a larger one, its stars forming bridges between the two. To early astronomers, these scenes looked like accidents. Today we know they are messages written by gravity. In everyday language, galaxies are messy storytellers, and their scars are the punctuation marks of cosmic history. When one galaxy passes near another, their mutual gravity distorts each structure. Stars are pulled into long tails and loops. Gas is compressed into knots that ignite with new star formation. Sometimes the collision is slow, creating elegant ripples that persist for billions of years. Sometimes it is head-on, merging both galaxies into one. The universe is full of these interactions, but only a few are captured in the act. Those become the pages of the atlas. Take the peculiar galaxy, NGC 7252, nicknamed the Atoms for Peace galaxy because its looping arms resemble the symbol of orbiting electrons. It is the aftermath of a merger between two spirals. The chaos has settled into a new order, with young clusters of stars glowing where the streams of gas collided. Observing such galaxies gives astronomers a time machine, showing what happens between the stages of collision and calm. Our own Milky Way and Andromeda will likely resemble this in 4 billion years. Another case is the Cartwheel galaxy. Struck by a smaller companion that plunged through its center, the impact sent a wave of compression outward, creating a bright ring of star formation that expands like a ripple in water. The ring structure will eventually fade, leaving behind a more conventional shape. But for now, it is a vivid record of an instant of violence. Simply put, peculiar galaxies are not anomalies, they are snapshots of transformation. They also serve as lenses into the invisible. Some of the strangest shapes in the atlas are not caused by collisions at all, but by the warping of light as it passes through massive clusters. Gravitational lensing bends and magnifies the light of distant galaxies, turning single points into arcs and mirrored images. These distortions reveal both the distribution of visible matter and the presence of dark matter, the unseen mass that makes up most of the universe. To put it another way, the peculiar is often the lens through which the normal becomes visible. When the Hubble Space Telescope began its deep surveys, it discovered entire fields of such lensed galaxies. Some appeared as thin blue arcs wrapped around invisible centers of gravity. Others were stretched into rings, the so-called Einstein rings, where alignment between source, lens, and observer is exact. Each distorted image provides data about the mass and shape of the intervening cluster. By analyzing them, astronomers can map the dark matter that otherwise leaves no trace. Why it matters is clear. These warped images are the most direct evidence we have for the large-scale skeleton of the cosmos. The peculiar shapes are the shadows cast by invisible structure. But the atlas extends beyond gravitational tricks. Peculiarity also comes from extremes of energy and form. There are galaxies with double nuclei, likely formed by two supermassive black holes not yet merged. Others contain vast plumes of gas extending hundreds of thousands of light-years, remnants of ancient jets. Some host starbursts so intense that they exhaust their gas in mere millions of years, burning bright and short. Every deviation from the norm exposes another way the universe experiments with form. Think of it like this. The universe is an artist with infinite canvases, and the peculiar galaxies are its sketches where imagination ran wild. The patterns uncovered by this atlas reveal an underlying unity. The same gravitational physics that creates spiral arms also sculpts tidal tails. The same feedback from black holes that shapes ordinary galaxies can drive the immense outflows seen in the extreme ones. The equations are the same, only the conditions differ. Peculiarity is a matter of context. In studying these systems, astronomers have begun to understand that the universe's apparent order is built from the remnants of chaos. Every symmetrical galaxy was once peculiar. Over time, interactions smooth their edges, mix their stars, and hide their scars. If we could rewind the clock, we would see every galaxy pass through strange and violent phases. Why it matters to us is philosophical as much as scientific. The universe's beauty is not born from perfection, but from imperfection resolved over time. The peculiar teaches us resilience, the tendency of matter to reorganize after disruption. Without collisions, there would be no grand spirals, no rich clusters, and no diversity of form. Our own galaxy owes its character to such encounters, its disk warped, its halo filled with streams of devoured companions. At its core, the Atlas of the Peculiar is a record of process, not category. Each entry is a reminder that nothing in the cosmos stands still long enough to remain ordinary. Some peculiar galaxies even act as cosmic amplifiers. When light from the early universe passes through their distorted gravitational fields, we gain magnified views of galaxies otherwise too faint to detect. Through them, we glimpse star systems forming when the universe was only a fraction of its current age. The peculiar becomes a telescope. The accident becomes an instrument. Simply put, the universe uses its own flaws as tools of revelation. As instruments advance, we continue to expand this atlas. The James Webb Space Telescope and next-generation observatories reveal new examples each month, galaxies whose morphologies defy old classifications. Some appear to be hybrids between spirals and irregulars. Others are so distant that their light began its journey before the Milky Way existed. Each discovery rewrites the margins of the map. Why it matters is that these peculiarities remind us that knowledge is always provisional. What seems exceptional today may tomorrow become typical as our sample grows. The boundaries between normal and strange are not fixed. They shift with every observation. In the grand view, the Atlas of the Peculiar is a testament to curiosity. Instead of discarding anomalies, astronomers turn them into guides. Every warped ring, every doubled image, every disturbed spiral adds a line to the story of how structure emerges from turbulence. Together, they trace the cosmic web itself, the vast network of filaments and voids that connect all galaxies. At its deepest level, the peculiar is not the exception but the connective tissue of reality. When we look up and see an arc of faint light stretched across the dark, we are not seeing error. We are seeing evidence of gravity's handwriting, of the invisible threads that tie galaxies into clusters and clusters into the web of the cosmos. The beauty of the peculiar is that it reveals what the ordinary conceals. The next and final act will step back from the map entirely, asking what these discoveries mean for us as observers living inside the picture, and whether the act of mapping the universe changes the meaning of our own existence within it. From our place within the Milky Way, every discovery we make about the universe is also a discovery about ourselves. We began by mapping what we could see, mistaking proximity for understanding, and yet with every instrument we built, the picture became stranger, not simpler. We found collisions where we expected calm, youth where we expected age, structure made of motion, an order that came only from chaos. The farther we look, the more the universe resembles a living mind, full of feedback and memory, self-correcting yet never still. In the dark between stars, the light from our instruments records more than data. It records a story of how knowledge unfolds in spirals. We draw closer to the truth, only to find that the truth has changed shape in the act of observation. The Milky Way's map is no longer a static image, but a pulse, a breathing record of evolution. Every orbit, every collision, every star born or lost, adds another heartbeat to the cosmic rhythm. At its core, the universe is not an archive, it is an improvisation. We used to think the sky was an inheritance, a set of facts waiting to be discovered. Now we know that observation changes what is known. A map of the galaxy made today will be different from one drawn tomorrow, not only because our instruments will improve, but because the galaxy itself will have shifted. The house we live in moves as we sketch it, walls changing shape, corridors opening and closing. The cartographer and the structure are the same process. In everyday language, the universe is drawing itself through us. This realization dissolves the border between science and philosophy. The act of seeing becomes participation. When we measure the Milky Way's stars, we are measuring motion that once shaped our planet, energy that will someday influence new worlds. Knowledge, in this sense, is not a possession but a current flowing through time. Every collision described in earlier chapters, every burst of radiation or ripple of gravity, reveals a deeper lesson. Creation and destruction are not opposites but partners. A galaxy grows by consuming. A star lives by collapsing. And even space expands by stretching the fabric of what once was whole. The laws of physics are not about preservation. They are about transformation. Why it matters reaches beyond astrophysics. It touches the logic of existence itself. We crave permanence, but the cosmos offers only change. Still, within that change lies continuity. The atoms in our bodies were forged in supernovae, shaped by long-dead stars, recycled through dust and gas into new forms. We are living evidence that destruction is not an ending, but a transition. Think of it like this. We are the Milky Way made self-aware, the galaxy looking inward to understand its own origins. This is the quiet revelation that waits behind all data. Science, at its most honest, is not the cataloging of things but the contemplation of motion. Every pattern we describe is temporary. Every certainty is a snapshot. The galaxy teaches this humility with every new discovery that overturns an old one. We once believed we occupied the center of everything. Then we learned we are off to the side of a spiral arm, on a small planet orbiting an ordinary star. Yet the demotion was not a loss of meaning. It was an expansion of it. We are not central, but we are connected to everything. That connection, not location, is what gives us significance. Simply put, meaning is scale independent. In the Milky Way's structure, we find an echo of our own experience. The thin disk, always forming new stars, mirrors the renewal of ideas. The thick disk, shaped by ancient collisions, holds the memory of what came before. The bar at the core, channeling material inward, is the heartbeat of curiosity itself, drawing questions toward the center until they collapse into understanding and explode outward again. The galaxy is not only a home, it is a metaphor for thought. As our maps grew sharper, we learned that our errors were not embarrassments, but steps in a recursive process. The misdrawn arms of early astronomers were not failures. They were iterations. Their mistakes defined the direction of the next correction. The same principle applies to us. Every theory, every model, every belief is a temporary construction awaiting revision. The value lies in the revision, not in the illusion of completeness. At its core, science is the art of being wrong in the most productive way possible. Why it matters once more comes to the human scale. When we recognize that the universe is an evolving system of feedback, we see ourselves not as detached observers, but as participants in that evolution. Our consciousness is an emergent property of the same physics that drives galaxies. Thought is a form of cosmic weather, shaped by matter and energy. Brief but real. To understand the galaxy is, in a small way, to understand ourselves as phenomena of the same order. There is a subtle comfort in this. If the Milky Way can renew itself after collisions and chaos, so can we. If the galaxy's center, once thought cold and old, still hosts the birth of new stars, then perhaps age, too, is not the end of creation but a different mode of it. We mirror the processes that built us. In plain terms, the cosmos is not indifferent. It is recursive. It teaches through repetition until we notice the pattern. The galaxies we observe, the light we collect, the theories we test, all point to a universe that thrives on impermanence. Change is not a flaw. It is the fundamental constant. The spiral that does not spin is still a spiral because the pattern endures while the components move, meaning works the same way. The words change, but the story persists. Consider the image of a gravitational lens. Bending light from a source we cannot see. To an untrained eye, it looks distorted, an error in the image. But to us, it reveals something hidden, a truth that only appears through curvature. Perhaps consciousness itself is a kind of lens, distorting and clarifying at once, turning the raw light of existence into a pattern we can recognize. At its quietest level, the universe may not need us to see it, yet by seeing, we complete its expression. Observation is the final act of every phenomenon. Without a witness, energy disperses unnoticed. With a witness, it becomes story. We are the witnesses of the Milky Way's unfolding, and the Milky Way, in turn, is the witness of the universe through us. In this perspective, humility becomes awe. The darkness above is not emptiness, but potential. The light from distant galaxies is not ancient history, but a continuous dialogue. The cosmos is speaking in spectra, in gravity, in time, and we, by listening, add another voice to the chorus. The final truth is simple but unsettling. The more we learn, the less we can claim to know completely. But that uncertainty is not failure. It is freedom. It keeps the conversation alive. It ensures that the universe, like thought itself, never ends. Somewhere beyond the edge of our current map, the unknown still waits. It is both question and invitation, shimmering like the faintest star at the limit of our instruments. If the universe keeps rewriting its own story, what chapter will it write through us next?